We are up to section 3.4 in Math 1325, and this is the final section of this chapter. So next week we'll be doing section 4.1. Two things from last time. Number one is if you do average rate of change, this is just like slope in algebra. And they write it a different way than algebra does, but it's in essence the same thing. F of B minus f of A over B minus A. And this is also how you find the slope of a secant line that crosses a curve twice. If you come through and touch there, and then keep going and touch there, touching twice. A secant line touches the curve twice. The second thing we did was instantaneous rate of change. Instantaneous rate of change. This is when you're at one specific point. And then this is for a tangent line. And one, I was trying to come up with something like slope. One application of it is velocity, actually. So how fast an object is moving is its instantaneous rate of change. And this is where you do limit as h approaches 0, f of a plus h minus f of a all over h. And this is a tangent line. If you have a curve and you want to touch it at one spot exactly, and you draw a tangent line that just touches it at that one spot. And the a here is some given number to you, so they give you one a value. A is a given value, where in number one, a and b are both given. There's two given values. So they'll tell you to go from like x equals 2 to x equals 8. In number 2, they tell you to go from x equals 2, for example. Those two are taught in 3.3. 3.4 is a continuation of number 2, and this is a concept called the derivative. The second major concept of calculus. The first major concept was limits that we did earlier in this chapter. The second major topic is called the derivative. It's really the same thing as instantaneous rate of change. So it's the same as number 2. It's just that number 2, you do that at one specific given a value. Now we're going to do it in general for any given x. So we're going to do this for x in general, not for a specific single number value. But other than that, it's really the same thing. So you do limit as h approaches 0. Same as right there. But instead of having a's right here, some single value like 2 or 6 or whatever number they give you, you just put x's there instead. F of x plus h minus f of x all over h. And the advantage of doing this generally first instead of specifically for one x value is if you just wanted to say, oh, I only want to learn number 2, I won't worry about number 3. The problem is every time you get a new x value to go to, you have to redo all the work all over again. But if you do this limit process that takes a while one time, then you, for any given x, you can just you just go right to the answer from there. So not for this first problem, but when we get to number 2, see, they want me to find the derivative, and the symbol for that is f prime of x. They want me to do it in terms of x first in general. But after you do all that, that'll be very similar to the previous section when you did instantaneous rate of change. But once you get the answer in terms of x, then it's very easy to do for 1 and do for 2 and do for 3. I don't have to repeat all that messy work 3 different times. It's just going to be one messy time, and then you just plug 1, 2, and 3 in and you get answers real quick. Okay, back to this though. Number 1, they want you to estimate the slope of the tangent line to the curve. That's because they're trying to get at the idea that the slope of a tangent line, that's what derivative is. So it's, I should add that here, slope of a tangent line. Anytime you hear slope of a tangent line, that's code for derivative. It's also the same thing as instantaneous rate of change, but a broader term for it in calculus is derivative. And the symbol is, if you have f of x given to you, you write f, one symbol for it is f prime of x. You put a little apostrophe, that means prime, or is red prime. F prime of x, when somebody sees that, they know, okay, they're talking about the derivative of f, not the original function. So this first problem, they're just trying to relate this to the previous section, that if you do the slope of a tangent line, that's the same thing as derivative. So if I blow this graph up, and this just says estimate it, you could use the formula for slope too, but so they give us one exact spot, -3, 1. We just have to find another exact spot on the pink line. It looks like that might be one right there, or even definitely right there. So whether you go up 2 to the right 1, 2, 3, 4, that works, or up 1 over 2, because up 2 over 4 reduces to up 1 over 2. So this is a slope of 1/2. So the instantaneous rate of change at that spot is 1/2, positive 1/2, and the derivative at that spot is 1/2, which just means the slope of the tangent line has a slope of 1/2. Because if I move to other spots on the curve, the slope of a tangent line will change. On a curve, the slope of a tangent line will change as you move across the curve. So it can go from flat to steep, or it can even change to negative or be 0. Okay, so now this will seem hopefully similar to the last video. In number 2, I'm given f of x, and it's -x squared plus 8x minus 9. And you had something like this last section too. Just there, they would say go at a equals 2, for example, or a equals 6, or whatever a value they'd give you. So now there is no a value given. We want to do this in general, not specifically for one x value. So f prime of x, that's the derivative of f. It's the limit as h approaches 0. You do this exactly the same way, you just leave x in there instead of putting an a value in. So f of x plus h rather than a plus h. Last time we did a plus h, now it's x plus h. Minus f of x rather than f of a, all over h is exactly the same thing, just x's instead of a's. So when I plug x plus h in to these x's, remember this, how I have my two brackets? So the first bracket, I'm going to have this negative right there. Then I'm plugging in x plus h for the x. That's one part that confuses especially algebra students. If there's just a 2 here, they know to put a 2 there, but if there's variables, then they start getting confused, especially when one of the variables is the same as what's already here. But this old x goes away, and it literally gets replaced by whatever's here. You don't care what's here, you just write it down, and then squared. The old x is gone. Plus 8, and then this old x goes away and gets replaced by x plus h. Minus 9, there's my first bracket. It's going to work out similarly to how I did the other ones. And you may remember last video, I mean, that whenever I had stuff that could be put together, like terms that could have been put together, usually I didn't do it because here you don't get like terms here. So that's why I left those alone, so that it would be very similar to this. So minus, here comes the second bracket. Now this is very easy here because f of x is what goes in the second bracket, and you don't have to even plug anything in or go searching. It's literally the problem that they told me. So the second bracket's even easier than last time. You just literally rewrite whatever the given function is inside the second bracket. Whether it has one term, two terms, three terms, this one has three terms. Doesn't matter. All over h. We have the same issue as last time, that we can't plug 0 in because it's going to make the bottom 0. So somehow we have to get rid of that bottom h. Okay, this is similar to yesterday. I'm going to do this little shortcut where you square the first term. You multiply this together and double it. xh is just xh, and double it 2xh. And then you square the last term, h squared. That's how you square a binomial. Then there's a negative that has to go to each one. So negative x squared, negative 2xh, and negative h squared. Plus 8x, plus 8h, minus 9. That's the first bracket right there. It's got 1, 2, 3, 4, 5, 6 terms, and this time none of them are like terms. None of these go together. Last time in the section 3.3, usually some of this stuff was like terms, but now they're not going to be. And that's why I didn't put them together last time. And then just like last time, you're going to put the negative on all three of these things. It's going to make them all switch. And just like last time, they should have a counterpart that they cancel with. That's your double check. So this negative x squared will turn to positive x squared here, and then it better have a negative x squared to cancel with it. Yes, it does. The positive 8x will turn into negative 8x, and then it better have a positive 8x to cancel with. Yep. The negative 9 will turn into positive 9 and cancel with the negative 9. If your whole second bracket doesn't cancel, you did something wrong. So that's always a nice little double check. All the remaining terms should also have h in them, and they do. There's an h here, here, and there. So then I can factor out a greatest common factor of h. Take this h away, you have negative 2x left. Take one of these two h's away, there'll be 1 left. Take this h away, and you just have plus 8 left. Just like last time, the h's cancel, and you plug 0 in for h. Now, in a college algebra class, they make students do this exact problem, except there's no limit going on because they don't know what a limit is. And in college algebra, we would say the answer is negative 2x minus h plus 8. That's called the difference quotient in algebra. But in calculus, we plug 0 in for h, and it makes that part go away, and you're just left with negative 2x plus 8. So everything on this page is algebra, except the very last step when you plug 0 in for h, for the limit, which is the easiest step of all. The h just minus 0 goes away. So this is the derivative right here. The original function f of x is negative x squared plus 8x minus 9, which is an upside down parabola. Something like this. And then the derivative is f prime of x equals negative 2x plus 8, which is a line. So this is what's nice, is by doing this in general first, instead of for one specific x value, I only had to do all this messy stuff one time. And now I can plug in 1 or 2 or 3 or negative 5 or positive 10. You can plug in as many different x's as you want. They're all going to go real quick. So the derivative, and they already have the f prime of x waiting in the answer. Negative 2x plus 8. So now doing f prime of 1, f prime of 2, f prime of 3, they all go extremely quickly. I don't have to redo all this if I would have done all this, if a was 1, I could have done this where a was 1 if I wanted to. That would have been just like last time. But then when I wanted to do 2 next, I'd have to redo everything with 2 and redo everything with 3. Instead, I can just come here and go f prime of 1, stick a 1 in. Negative 2 times 1 is negative 2, plus 8 is 6. F prime of 1 is 6. Then I can plug in f prime of 2 and put a 2 here. F prime of 3, put a 3 here. So f prime of 1 is 6. F prime of 2 would be negative 2 times 2 is negative 4. Negative 4 plus 8 is 4. And then plug in 3. Negative 2 times 3 is negative 6, plus 8 is 2. See how fast those other ones go? That's what's nice about having it in general. Then you can plug in as many as you want. Okay, 48 over x is the original function for number 3. F of x equals 48 over x. If you get a rational function, this is done a little bit differently. But same starting point. Limit as h approaches 0. This is going to be f prime of x. It's f of x plus h minus f of x all over h. Well, there isn't a whole lot of bracket stuff here. The first bracket is literally just putting this in for this x right there. And you just get 48 over x plus h. That's the whole first bracket right there. And then minus the second bracket is the original function itself, 48 over x. That one you never have to think about. You just, whatever the problem is, that's what goes in the second bracket. All over h. So there's nothing that goes together very nicely here. I can't plug 0 in because it makes the overall denominator 0. So really all we can do at this point is try to get common denominators out of this and this. And there's no easy way to create a common denominator when something has an extra plus or minus in it. So the only common denominator is to take each fraction and multiply top and bottom by the other's denominator. If I multiply the first fraction by x over x, and then minus 48 over x, and then I'm going to multiply the second fraction by this denominator over itself. Each fraction gets the other's denominator. Whenever you have two completely different denominators, that's the only way to get a common denominator. You multiply each one by the other one. And that way both of them will have this for a common denominator. And then of course we're over h. So we end up getting, this is just 48x. Now be careful here, this always tricks people. Whenever you're doing a 48 times something where you're going to need to distribute it, if there's a minus out here in front of the fraction, that really goes with both of them. So it's very common to miss the second sign. So what I do is I change this minus to a plus by bringing the negative up here with a 48. Adding a negative is the same thing as subtracting. So it's actually negative 48 times x is negative 48x, which most people see. But a lot of students miss this part. Negative 48 times h is negative 48h, not positive. So watch out for that sign right there. That's a very common error in calculus, in algebra really, but it happens in calculus a lot. So then we're all over h. We still have this h in the denominator that's causing all the problems because I can't plug 0 in yet. But notice here, this 48x and this negative 48x cancel. So I'm left with limit as h approaches 0 of negative 48h over h. And now that there's no longer multiple terms in the top, then you can cancel this h with this h. This h does not cancel that one as long as this stuff's still here. You can never cancel individually when there's multiple terms in part of the fraction. So I get negative 4, the limit as h approaches 0 of negative 48, and there is no h left. The limit of a constant is the constant itself, so the answer is negative 48. And, oh no, wait, I missed something. I know I missed something because I forgot to put the common denominator is what happened. So let me rewrite where I was. So limit as h approaches 0. So it's right here. I forgot to put, I was so focused on the canceling part, I forgot this common denominator right here. So I'm going to rewrite this. So at that point, I should have had 48x minus 48x minus 48h. This goes over the common denominator. I forgot that. And then it's all over h. So this still does cancel, but these h's don't cancel right away because we have this right here. So we're left with limit as h approaches 0 for negative 48h over the common denominator. That's a fraction by itself. And then it's all over h, or what you could write as h over 1. So that way we have a fraction divided by a fraction. Remember my little poem that goes, when dividing fractions, don't be shy. Flip the second and multiply. That gets rid of the entire denominator, so you don't have fractions inside of fractions anymore. Now, at this point, I would still be in trouble with plugging 0 in for h right there, but now because this is just one term, this part here does not have multiple terms that are added and subtracted, then you can cancel this h with this h. You can't cancel this h with this one because there's a plus right there. So you can only cancel when everything surrounding what you're canceling is multiplied or divided. So not when there's pluses and minuses, which causes the problem here and right there. So I thought I was having a brain cramp and I forgot my common denominator actually. So the answer is not just negative 48. That's the numerator part. This is still here. And you could distribute this if you want or not. It doesn't really matter. Because now we're ready to plug 0, and even though this h is in the bottom, it's not just h in the bottom. So then you get negative 48 over x times x plus 0. X plus 0 is x, and x times x is x squared. So here's the derivative answer. F prime of x is negative 48 over x squared. The original function was 48 over x. The derivative is negative 48 over x squared. Now we can plug various numbers in. So if my original function is 48 over x, and the derivative function f prime of x is negative 48 over x squared, they want you to do f prime of negative 4, 0, and 2. So this is what's nice, is I don't have to go back and do all this all over again 2 more times. If I would have just plugged negative 4 in for x, I would already have this part A answer, or part B, I guess it is, but we could already have the answer to this if we would have plugged negative 4 in here instead of using x's. But then when we wanted 0 and 2, we'd have to redo all that work. So now this just goes a lot quicker. I can do multiple x's, as many as I want, real quickly. So negative 48 over negative 4 squared. Now keep in mind, anything squared is positive. but this negative 48 is going to be over positive 16. So that makes negative 3 for the answer. And then negative 48 over 0 squared, that's negative 48 over 0, which is undefined. You can't divide by 0. Derivatives are sometimes undefined. In fact, there's a homework problem where they give you a graph and they say, tell me all the spots where the derivative doesn't exist. So we're going to learn that in a minute, but I'm going to show you what this is related to. Negative 48 over 2 squared is negative 48 over 4, which is negative 12. So the three answers we're looking for here are negative 3. When it does not exist, when it's undefined, you just say the derivative does not exist. Remember, they do that for limits too sometimes, but it's actually more common to say undefined when functions don't have answers. And then this one was negative 12. So what does all this mean? This may be a graph you remember from college algebra. This is just the good old reciprocal function that's been vertically stretched. But it sort of looks like this. And if you go to negative 4, 1, 2, 3, 4, this spot right here, if you draw a tangent line at that spot, the slope of this tangent line is right there, negative 3. The slope of that line is negative 3. Notice it's negative because it's going down left to right. And when you get to 0, there's nothing in the graph exists at 0 because there's a vertical asymptote there. So anytime you're at a spot on a graph where there's literally nothing there, the derivative can't exist at those points. The derivative doesn't exist at any spot the regular function doesn't exist. So that could be vertical asymptotes, it could be holes in the graph, it could be like a square root function. A square root function doesn't have any holes or asymptotes, but it just goes to the right of 0 only. There's nothing going on over here on the negative side. So if you did the square root function and found its derivative and then said, what's f prime of negative 2? It's going to be undefined because there's nothing in the regular graph over there. And then finally at positive 2, which is about here, so we would be about here, I'm guessing, estimating. Notice that this would have a much steeper negative slope than the first one did. And that's why it's negative 12. Negative 12 is steeper than negative 3. This would be a slope of negative 12. This is a slope of negative 3. Negative 3 is flatter. Negative 12 is steeper. If I would have went to positive 4, that one might mirror negative 4, and that one might have a negative 3 also. So that's what these derivatives are used for, is they quickly get us the slope of tangent lines. Okay, one more example from the same kind of problem where they want me to do the derivative in general first and then plug in 3 values after that. And we've done a squared problem, quadratic. We've done a rational function. Number 4 is for a cubic function. 2x cubed plus 6. So limit as h approaches 0, f of x plus h minus f of x all over h. So my first bracket is going to be 2, plug in x plus h right there, to the third power, plus 6, and that's the whole first bracket. There could have been a squared term and an x of the first term, but luckily there isn't, otherwise it really gets messy. So minus, now do the original f of x, literally just like it looks. You just write it down in the second bracket, whatever is given to you. And once we put the negative on each of these two, they should cancel 2 of the stuff from this part. So x plus h cubed, remember I taught you how to do that quicker, x plus h cubed. When I get one of these binomials cubed, I use Pascal's triangle, row 0, row 1, row 2, row 3. So I'm going to have a 1, a 3, a 3, and a 1 from the third row of Pascal's triangle. The first term, whatever's right there, you put that first after each number. Multiplied in. And that's going to get the exponents in descending order, 3, 2, 1, and 0. And then you put the h after that, or whatever is in the second slot. And that gets the exponents in reverse order, 3, 2, 1, 0. Notice the sum of all exponents. 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2 is 3, and 0 plus 3 is 3. They always have the same as the original exponent. And then when there's a plus here, you get all pluses here. In fact, because the definition of the derivative has a plus here, you're always going to have all pluses for these problems. If there's a minus here in general, then you get plus, minus, it just alternates. But in the definition of derivative, there's always a plus here, never a minus. Okay, then I like to cross out the 0 powers, because that equals 1. Cross out the 1s. Now, if there was nothing left, then you would have to put a 1, but you can cross out the 1s if there's other stuff here. There's something here. There's an x to the third here. And this problem's easier than the one we did last time because this is really the answer right there. There's nothing to simplify here. It's literally 3x squared h to the first is h. And same thing here. This is 3x h squared. And this is just h to the third. So it's x cubed plus 3x squared h plus 3x h squared plus h cubed. It's sort of symmetrical. So I'm going to write it here just so you can see it better. X cubed plus 3x squared h plus 3xh squared plus h cubed. Because then you need to distribute this 2 into it. So limit as h approaches 0. Here comes my first bracket. I'm going to drop the brackets at this point, but this is coming from the first bracket. 2x cubed, 6x squared h, 6xh squared, and 2h cubed. And then, of course, this plus 6. So the first bracket produced 1, 2, 3, 4, 5 terms. There's only 2 terms here. So after I put the negative on each one, they should cancel 2 of these 5. So the positive 2x cubed will turn into negative 2x cubed and cancel with positive 2x cubed somewhere. Yes. The positive 6 will turn into negative 6 and cancel the positive 6. Sometimes a student is so focused on doing all of this and distributing the 2 into it, and they forget about this little plus 6 right here. And then the double check would tell you, oh, wait a minute, I got a minus 6. Where's the plus 6? Oh, wait, it's up there. So sometimes that happens. Okay, all the remaining terms have an h. So we can pull out limit as h approaches 0. We can pull out an h that will eventually cancel the bottom h. Take this h away right here. You would just have 6x squared left. For the 6xh squared, take one h away and you would still have 6xh. And then finally the 2h cubed. Take the 1h away, there would still be 2 left, so 2h squared. Boom, boom, those are gone. And now you can plug 0 in for h. And 0 squared is 0, times 2 is 0, and plus 0 doesn't matter if there's other stuff. 6x times 0 is 0, plus 0 doesn't matter. You literally just get this left over. So f prime of x, the derivative in general, is 6x squared. All the other parts disappeared. And now plug in -1, 0, and +1. 6x squared is all we had left. Everything else either canceled or disappeared when I plug 0 in. So this is nice because whether you plug in 1 or -1, as soon as you square that, that goes to +1. -1 squared or +1 squared, they both equal 1 times 6 is 6. And then 0 squared is 0 times 6 is 0. Not undefined, but 0. And then, of course, this one's 6, because squaring 1 or -1 gives you the same answer. Now, maybe you remember in college algebra how 2x cubed plus, what was it, plus 6? Is that what we had? Yeah, 2x cubed plus 6. This is a graph that's shifted up 6. And it's vertically stretched by 2, but other than that, it's a cubic function. When x equals 1, your tangent line would be right there, and that's going to go like so. And apparently that is a slope of 6, because that's the answer I got. You can't exactly tell that from a sketch of the graph, but the answer was 6 here, so that I know that's 6. And then by the symmetry of the graph, the same thing happens right here. Now again, I'm just estimating, but this should be parallel to the other one, because the answers, they both had an answer of 6 for their slope. So the tangent line is 6 here, it's 6 there, but if you move to other spots like here, it's even more steep. If you come here, it's a little flatter. So only at these two spots, apparently, is it exactly 6. Everywhere else, it's going to be different. And exactly at the y-intercept, if I blow this up a little bit, a cubic graph curves up and it's flat for just a very slight moment in time before it goes back up again. So literally right there at the y-intercept, the tangent line is horizontal. It's flat for a moment at that spot. And I definitely know that because the answer to this was 0. A 0 slope is horizontal. So these three answers that I just got are confirmed if you have college algebra knowledge of what's happening to this graph. Now, the other point of this is if you don't know what the graph looks like the first problem we did, number 2, maybe you don't know, I just drew a quick sketch of this thing, but this may not be what it's actually shaped like. There's a -x squared, a plus 8x, and a -9. The -9 is the y-intercept, but it's not the vertex actually. So this parabola might go like through -9 and come over here, and there might be a vertex over here or something. So this one was a little harder to check until you looked at the graph a little longer. But that's the point, is even if you don't know what the graph looks like, you can still get all these answers. All this stuff here tells me what's going on, even if I don't know what the graph looks like. Okay, so find the equation of the secant line, and then find the equation of the tangent line. Okay, so the secant line f of x equals x squared plus x. To do a secant line, you need 2 given values, and that's what they did, is they said x equals 1 and x equals 3. The secant line slope is the slope from algebra. F of b minus f of a over b minus a. So the bottom's easy, 3 minus 1. If I plug 3 in, 3 squared is 9, plus 3 is 12, f of 3 is 12. Plug 1 in, 1 squared is 1, plus 1 is 2. This is 10 divided by 2. This has a slope of 5. So x squared plus x, that whatever that quadratic graph looks like, from x equals 1 to x equals 3, there would be a secant line through those 2 points because it's curved there. I didn't draw the best picture there, but they want the equation of this secant line. Well, an equation of a line is always y equals mx plus b. We know the m, it's 5. I just did what we did the last time in section 3.3, the average rate of change to get the slope of the secant line. Now, the secant line apparently crosses the y-axis down here. So if my sketch of my graph is even close to the real one, then this should have a negative y-intercept. And in order to find it, all you have to do is plug in either 1, 2, because that's what I got when I plugged 1 in, or 3, 12. This point right here is 1, 2. This one's 3, 12. So 1 and 2 sounds better than 3 and 12. I would put 2 in for y and 1 in for x with 5 in for the slope, and then you can solve for b. So you just temporarily plug in for x and y till you find b. So 2 equals 5 plus b. Subtract 5. And b equals negative 3. So 5x minus 3, that's the equation of the secant line. Y equals 5x minus 3. We're not just looking for the slope. That's what we've been doing up to this point. Now they actually want the equation of it, which uses the slope. So it's the next natural thing to do after you learn slope is to get the equation of a line. But that problem, there was no calculus involved in that entire part. Part A is all algebra. Part B, equation of the tangent line, that's calculus, although it's filled with algebra too. So now we just have to do limit as h approaches 0 for f of x plus h minus f of x all over h. And the function is x squared plus x. We can do it in general first. Okay, so my first bracket, x squared plus x, I'm going to put this in for the x squared, x plus h squared plus x, then put this in for x. The whole function was just x squared plus x. There was no plus something or minus something in the back. So we put x plus h here, and it's squared, and then we put x plus h there. And then the second bracket's easy. You just put the x squared plus x, the given function, all over h. We've done this a number of times. You're going to get an x squared, a 2xh, and an h squared. And then you still have your x and h. Usually there's a number. Sometimes there's a number here to distribute in, but we don't have one. So my first bracket produced 5 terms. And then I've got 2 terms in the second bracket. So once I put the negative on both of them, they're going to cancel 2 of these 5. So the x squared switches the negative x squared and cancels positive x squared. The positive x switches the negative x and cancels positive x. All the remaining terms have h in them. So pull out an h, there would be a 2x left, a plus h, and this, since you're taking the h away, you can't leave it blank, so it's plus 1. If there's 3 terms you're factoring, there should be 3 terms in the parenthesis. Some people forget to put the plus 1. So the h's cancel. I can plug in 0 for this h, and all that's left is 2x plus 1. So the derivative of this function in general is 2x plus 1. If f of x equals x squared plus x, f prime of x equals 2x plus 1. They want me to find the equation of the tangent line at the first value. It could have been any single spot, but they happen to pick the first one, which is 1. So this was, let me blow this up a little bigger. We had this parabola, and the secant line went through twice, here and here. This had an equation of y equals 5x minus 3. This is the minus 3 right there, because the x-axis should be like this, although I don't have it drawn properly. But it does go through the origin. This is supposed to be 1, 2 right here, and this is 312. So this is the secant line. It had a slope of 5, so the equation has 5x, and it crosses the y-axis at -3. But if I come right to this spot only and draw a tangent line there, it's going to have a less steep slope. And I can tell what the slope is by doing f prime of 1. F prime of 1 is the slope of the tangent line when x equals 1. 2 plus 1 is 3, so my drawing isn't perfect, but maybe here it would look better if I drew it right there. This slope is 5, this slope is 3. It's clearly less steep, so that makes sense actually. So this line has a slope of 3 by plugging 1 into the derivative function. So then I know the equation of it is y equals 3x plus or minus something. I don't know the y-intercept yet, although maybe it's slightly negative. But we can do the same thing we did a second ago. We can just say, okay, it's 3x plus b. Now, before we could have chose to use 312 or 1, 2. Now we only have a choice of 1, 2 because the tangent line doesn't go through 312. So I have to put 2 in for y. I would put that in anyway, and 1 in for x, just so you can solve b for b. So 2 equals 3 plus b. Subtract 3 from each side, and yeah, it's going to be negative. B is going to equal -1. So this is crossing at -1. This one's crossing at -3. This one has a slope of 3. This one has a slope of 5. And even a rough sketch of the graph confirms all that. Y equals 3x minus 1. That's the equation of the tangent line. So after you learn how to find slopes of secant lines and slopes of tangent lines like section 3.3, then they sometimes make you do equations of them, which takes you back to algebra, really. There's no calculus to that aspect. Okay, same kind of problem, but we're doing a rational function. So this will be our second example of this. The original function is 8 over x. They want the secant line between 2 and 8, and they want the tangent line only at 2. That's similar to the last problem. 2 and 8 for the secant line, and just 2 for the tangent line. So part A is about the secant line. So I need the slope of a secant line is just f of b minus f of a over b minus a. This is the same as average rate of change. The bottom of that's always easy because this is b and this is a, so literally 8 minus 2. If I plug 8 in, I'll get 8 divided by 8, so f of b is just 1. Plug 2 in, 8 divided by 2 is 4. So 1 minus 4 is -3. 8 minus 2 is 6, so the slope's -1/2. So the secant line definitely has a slope of -1/2. So it's definitely y equals -1/2 x plus something for the equation of it. And we do this in algebra all the time where they give the students the slope of a line and 1 or 2 points on it, and they have to come up with the equation. So you can either use 2, 4 or 8, 1, your choice. It doesn't matter which one you pick. The 1's better than the 2 or the 4, but the 8's higher, so it's really not going to matter. I guess I'll put in 8 for y and 1 for x. No, actually, I'm going to reverse it. I'm going to put 4 in for y and 2 for x. The reason I changed my mind was 1 times -1/2 is -1/2, and then you'd have to deal with fractions to finish it. By plugging 2 in, these 2's cancel, and you just get -1 here. So add 1 to both sides, and b equals 5. So the secant line, we already knew it had a slope of -1/2. It has an equation of y equals -1/2 x plus 5. And if you know what 8 divided by x looks like, 8 divided by x is basically the same as 1 divided by x, is just vertically stretched times 8. So it's a graph that looks like this. When x equals 2 and 8 is where we're going between. So let's say this is when, well, we know what the coordinates are. What were they again? 2, 4, and 8, 1 are the coordinates. 2, 4, and 8, 1 are the two coordinates you're going through. So 2, 4, let's say this is 2, 4 right here. And let's make this 8, 1. So there's a line that goes through those 2 points. And that line has a slope of -1/2. And we just found out the y-intercept is 5. Which actually makes sense, because if a slope's -1/2, you go down 1 and over 2. If you reverse that and go up 1 and 2 this way, going 2 this way takes you right back to the y-axis, because you were at 2, and up 1 is 5. So that's totally confirmed from this graph right here. The secant line equation is definitely y equals -1/2 x plus 5. That's where it happens to cross the y-axis. There's no calculus anywhere in this part A. That's all algebra right there. And the only calculus in part B is plugging in that h of 0 for the limit. And we did one of these previously, so here's a second example of it. And after you see this, you might discover there's a shortcut to this, but and that's how I knew I messed it up the last time. I was correct all the way down, and then I just brain cramp and forgot to put my common denominator. So limit as limit as h approaches 0, f of x plus h minus f of x all over h. So your first bracket, you're just putting x plus h in the denominator. So instead of 8 over x, you get 8 over x plus h. That's the first bracket. I'm not even going to put a bracket around it because it's the whole thing. And then minus the original function, which is just 8 over x, all over h. And because you have fractions in the top, you can put this over 1, so that way you have fraction divided by a fraction. So this one you multiply by the other denominator to the top and bottom, and this one you multiply by the other denominator to the top and bottom. So you get an 8x right here, and then I'm going to hopefully not forget this time. I'm going to put my common denominator here. That's what I meant to do last time. I forgot to do it. They both have this, so then you can be all in one common denominator. And then, of course, you still have the overall fraction where the h over 1's in the other denominator. And then I like to change this to a plus by making this a minus, and now distribute -8x and -8h. That sign right there can be missed if you don't do this little deal. In these rational function problems, this always cancels that. Once you do when dividing fractions, don't be shy. Flip the second and multiply. which gets rid of this, and you don't have fractions inside of fractions anymore. Because there's just one term right here, and the 8 and the h are multiplied together, then you can cancel this h with this one. And then once you plug 0 in for h, then the bottom just becomes x squared. So the derivative in general is -8 over x squared. When the original function is +8 over x, the derivative turns out to be -8 over x squared. That's kind of a shortcut some people realize. So then we want to do the slope only at x equals 2. They only care about the spot 2 right now. So if I put a tangent line right here at only at 2, not at 8, that's got a steeper slope to it, a steeper negative slope. So maybe that's -2 or -3 or -4, but it's clearly more than -0.5. And the y-intercept is clearly higher than 5 too. So by knowing a sketch of the graph, you can know what answer to expect. I'm going to plug in 2 to this thing, because that's the spot they told me to do this at. -8 over 2 squared, that's -8 over 4. The slope of the tangent line is -2. So that's this steeper slope is -2. And therefore the equation of it is y equals -2x plus something, or minus something, but in this case it's plus something. And you only have this coordinate to work with. This coordinate's not on that line. So now you don't have a choice. You have to put 4 in for y and 2 in for x and solve for b. And -2 times 2 is -4. Add 4 to both sides. 4 plus 4 is 8. So that's crossing at 8. And you're 2 away from the x-axis or the y-axis. So if you go up to left 1, up to left 1, that's when you'll land on the y-axis. And if you do up to twice, your 4 is going to go up to 8. So that makes sense. So the equation of the tangent line is y equals -2x plus 8. And they already have the y equals. Sometimes they don't put that and you have to put it, so be careful about that. But they already have the y equals here. Y equals -2x plus 8. So this is kind of good. Those problems 5 and 6. 5 and 6. They had both the secant equation of a secant line, equation of a tangent line, and it's really putting everything together from these last two sections. Okay, the next two are really quick problems. If you have a graph, like this little thing looks like the Texans symbol on their helmets a little bit. There's a number of things where derivatives do not exist or are undefined. I already mentioned if a graph doesn't exist somewhere, if the original graph doesn't exist somewhere, then the derivative can't exist there. So anytime you have asymptotes, vertical asymptotes, or holes in the graph, or like the square root function where it just doesn't exist in the negative side. Another example of that, log graphs only exist in the positive side of the graph. So a derivative of a log on negative x values will not exist because there's nothing in the original graph. So if you get a graph like this, though, that's continuous everywhere, there's no x value here where the graph doesn't exist or has some kind of issue like a hole in it. So then in theory, the derivative could exist everywhere. There's a couple of other issues. Another spot where you can't get a derivative is this right here, a corner point, because you can't draw a tangent line there. The tangent is kind of like negative for a while. Let me draw this out over here where it's bigger. So when you come around like this and then repeat that on the other side, you can get a tangent line right there to be negative. If you go here, it's a little more negative. If you pick this spot, then it's positive. This spot's positive but flatter. You can go to any spot and put a tangent line that's in theory parallel to the curve at that one spot, except at the corner point. because is it here? Is it there? Is it here? It's kind of like moving too much, and it's like moving in every direction at one time. So this makes it go haywire, and it doesn't exist there. So corner points are an issue for finding derivatives, in addition to spots where the graph just physically doesn't exist. So one place to look for is, does the graph physically not exist anywhere? That doesn't happen here. It exists everywhere. And then corner points is another spot. So when x is -1 on this graph, that's the one and only issue with this. If I tried to do f prime of -1, it would turn out to be undefined in some way. F prime of -1 is the only x value here I can't calculate if I knew the equation to the graph. So we want spots where the graph doesn't exist. So like this graph here, there's nothing going on the negative side of the graph. So any negative value is going to be undefined for the derivative. Although some ways they can get out of that issue is, notice up here they gave me a limited domain. 0 is less than x is less than 8. So they've already excluded all the negatives for that. And also notice nothing's happening in the graph bigger than 8 either. So otherwise we'd have a whole bunch of spots that don't exist. So they limited me to just 0 through 8, and we're not including 0, we're not including 8. So just move between 0 and 8. Everything exists between 0 and 8, so we don't have any undefined spots in there. If there was, we would include them in the answer. There is a corner point right there. That's an issue, right at x equals 2. So 2 is definitely a spot where the derivative would be undefined. If you can't calculate the derivative, they call it not differentiable. So in other words, the verb for a derivative is to differentiate. Differentiate is the verb for find a derivative. Or you can say it is differentiable or not differentiable. That's kind of like the action of it. So corner points, non-existent spots, there's a couple other things to look for. If you ever somehow had a vertical tangent line, a good example of that would be a circle. If you come to the far right or far left, a tangent line would literally be vertical in those spots. And vertical lines have slopes that are undefined. So if the slope of a tangent line is undefined, the derivative is undefined, because the derivative literally means slope of a tangent line. If a slope is horizontal, then it has a 0 slope, and then the derivative is 0. So that's a good spot, actually. But vertical tangent lines are no good. That's another one. And we don't have any on this graph. There's no spot that has a vertical tangent line unless this would have kept going around, but we already excluded this point anyway. And then finally, the last thing is if you have spots that are not continuous. Remember our continuity checklist? So in here, if you see a graph, it's easier to see if it's continuous than going through the checklist. But right there's an open circle, and then there's a closed circle below it. So that's why the function is defined there. But it's definitely discontinuous at the spot because I'd have to pick my pencil up to go on the other side of that. So any spot that's discontinuous, whether you can see it in a graph or whether you have to use the continuity checklist to figure it out, that will not have a derivative either because I can't get a tangent line exactly at the spot. You can't do a tangent line at a single point. You need some kind of line or curve to go around. So x equals 4 is another one. And then the same thing happens at 6 where it's broken apart again. So 2, 4, and 6. These are 3 x values between 0 and 8 where I would have issues trying to find the derivative. Those spots would not be differentiable, along with everything from 0 to negatives and everything above 8, which got excluded here because of the domain. Okay, finally we get 2 of these business application problems. So we have the demand of an item, D of P equals -4P squared minus 8P plus 300. P is the price of an item in dollars. Find the rate of change of demand with respect to the price. And notice there's no numerical value given for part A. So that means they want it in general, not for a specific value. And rate of change, that's slope, and slope at a given spot is derivative. So and it couldn't be secant slope because you would need two values given to you to do that. So rate of change, that could be secant or tangent line slopes, but clearly this one's for a tangent line. So that's your phrase to tell you, oh, okay, I need to do the derivative if they want the rate of change in general without any given values to me. Plus 300. So rate of change is slope, and slope can be secant or tangent, but this one's tangent. So this is telling me to do the derivative. Whoops. So notice this is d of p, so I'm going to write it that way, d prime of p, just to be consistent, instead of putting f prime of x. So limit as h approaches 0, I keep doing it, d of, and we got p's instead of x, I'm going to stay consistent with that too, p plus h minus d of p, which is the original function, all over h. So instead of putting f of x and f of x, I've got d of p because that's what's here. So my first bracket, we've done this numerous times. Hopefully you're finding this easier now, even if it's kind of long and messy. I've got my -4. Then in place of this p, I'm going to put p plus h squared minus 8 p plus h plus 300. That's the first bracket. The second bracket is literally what they say the original function is. That's what's nice when you do this in general. You never have to think about the second bracket. And then everything in the second bracket will eventually cancel all the mess we get from the first bracket. So this squared part will be p squared. I'll write it right below so I can distribute the -4. And then there'll be a 2ph and an h squared. So now I'm going to get, here comes the long first bracket with multiple terms. There'll probably be 6 terms here. -4p squared, -8ph, and -4h squared. Minus 8p, minus 8h, plus 300. There's 6 terms for the first bracket. There's 3 terms in the second bracket, so all 3 of these are going to cancel 3 of these 6. The -4p squared will switch to positive 4p squared. And there should be a -4p squared it cancels with. Yep. The -8p will turn into positive 8p and cancel with -8p. Yes. And the positive 300 will turn into -300 and cancel positive 300. Yep. Take away an h here, here, and here. Limit as h approaches 0. That will let you factor an h off the numerator, and it'll cancel with the denominator eventually. -8ph, I took the h away, so there's just -8p there. -4h squared, 1h went away, but then it'll still be -4h left over. And -8h, take the h away, the -8 will still be there. This h cancels that h, this 0 takes this whole 4h away. So d prime of p, which is the answer to part A, is -8p minus 8. This is how demand is changing instantaneously. Instantaneous rate of change is the same thing as derivative. So this is what's going on in the economy right now, how we have inflation going on and demand is going down as prices go up. So the rate of change of demand with respect to price, it's negative, -8p minus 8. So then what if I plug in $15? Because P is just dollars. Put $15 in there. Negative 8 times 15 minus 8. Negative 128. So when price is 15, the demand is decreasing because it was negative at a rate of about blank items for, and then each increase in price of 15 or $1. You always compare this to the price of $1 because it's price in dollars. So just for the 15's already over here, you don't put it twice. Now, when you say it's decreasing, I don't think you need to put the negative. I think you just say 128 here because decreasing by 128 means negative 128. If you technically put a negative there and said it's decreasing by negative 128, that's kind of like a double negative. So then you're kind of implying that it's increasing. So when you set your price at $15, demand decreases. So then maybe you have to lower your price if you want to increase demand. That's the law of supply and demand in business. Okay, so this final one here, number 10. Another thing they mentioned last time was the word marginal. The word marginal is code for derivative. Marginal revenue, or you can do marginal demand or marginal profits. Anything in business, you can do marginal for it. So we have R of X, that's the revenue. Revenue is capital R. Here's the revenue our business takes in. Revenue is how much money you bring in. It's not profits. But revenue is how much money comes in, and then you can have costs. There's also cost functions. Cost is what it costs your business to do your stuff. And then if you do revenue minus cost, that's your profits. So determine the marginal revenue. So this is just code for the revenue function is 41x. Whoops, forgot the x. 41x minus x squared over 200, or you could write 1/200th x squared, which actually might be preferred here. This is the revenue function. Part A says find marginal revenue. As soon as you hear that, you should be thinking derivative. So unfortunately, I got to do that derivative one more time. I'll do it on a separate screen so I can just keep all my parts here. So the original function is 41x minus 1/200x squared. Limit as h approaches 0. F of x plus h minus f of x all over h. So first bracket, 41, put in x plus h right there. Minus 1/200, put x plus h right there, squared. That's the entire first bracket. Second bracket is the original function. All over h. This part's easy, 41x plus 41h. We've seen this numerous times. This makes x squared plus 2xh plus h squared. But then you got to distribute a negative 1/200 to that. So negative 1/200 x squared. And that, when you do 2 times negative 1/200, that'll be negative 1/100. You're reducing the 2 with the 200 to 1/100. xh, and then negative 1/200 for the h squared. 1, 2, 3, 4, 5 terms this time. We only have 2 terms here, so these two are going to switch and cancel. The 41x will turn into negative 41x and cancel the positive 41x. the negative 1 over 200 x squared will turn into positive 1 over 200 x squared and cancel with the negative 1 over 200 x squared. 3 terms left. They all have h in them. So we can factor h out and cancel it with the bottom eventually. So 41h, take the h away. That leaves you just with 41. Negative 1 over 100 xh. The h went away, so it's just negative 1 over 100x. And this is negative 1 over 200. One of the h's went away, but there's still an h there. Negative 1 over 200h. This cancels this. This makes the whole third term disappear. That whole part will be 0. So the derivative is right there. Demand. Or no, it's revenue, sorry. So revenue, r prime of x equals, this is the part A answer, 41 minus 1 over 100x. This is part A. 41 minus 1 over 100x. So just because it was fractions and larger numbers, that kind of got a little messy, but it still came out nicely in the end. Okay, it says estimate the revenue from the sale of the 3001st table. This company makes tables, apparently picnic tables, by finding r prime of 3000. So if you do the derivative at 3000, this estimates how much you'll make after you. So the company's already sold 3,000 picnic tables. What if they make a 3001st table? How much money will they make just in the process of that one extra table? This is a way to estimate that. If you plug into a derivative the previous number, you get an estimate for what will happen for that one. So 41 minus 1 over 100 times 3,000. So 1 over 100 is the same thing as divided by 100. So I could do 3,000 divided by 100. That's the same thing as times 1 over 100. That's 30. So this part right here equals 30. 41 minus 30 is 11. That's the part B answer, 11. Estimate the revenue. Revenue, they would take in 11, whatever it is. Does it say dollars? Okay. So that's not very much for a picnic table, but okay. $11. Determine the actual revenue from this 3001st table. So that's where you just plug that into the regular function. If I plug 3001 into the original function, which is a little bit harder to do in this type of calculator, but I could do 3001 squared for the numerator, divided by 200, and then whatever 41 times 3001 is, you'll have to subtract this. So let me see if I can remember that number. Take a picture of it so I can remember it. 45,030.005. Okay, so now I need to do 41 times 3001. That's this part, minus this answer I just had, which was $45,030.005. Okay, so that doesn't seem to make sense though. Round to the nearest cent. Estimate the actual revenue from the sale of the 3001st table is given by this. So let me try something real quick here. What if we did 3? Try this. I don't think this is right, but okay, yeah. Use the fact that R is the revenue generated from the sale of X picnic tables. Okay, actual revenue 3001. 3001 squared divided by 200. Yeah. The reason I know something's wrong is because the point of this is these two parts are supposed to be relatively close to each other. So I'm not sure what we're supposed to plug in there. Let me check quick. So we got part A and B right. What's happening in C? Did that already? Okay, we got there's part A. So plug it in. That's easy. Part B. Okay. Find R of 8001 and R of 8000. Okay, so maybe just subtract those two. Okay. So the answer I got was almost it. There was just one step I was missing. So you need to do 3001 in the original function. That's what I did do, and I got that weird answer, so I knew something was wrong. 78,010.995. That's for 3001. So then you also do it for 3000. See, this is kind of like secant is the point here. In a tangent line, you do it at one spot, but for a secant line, you have to do it at two spots. So let's do a 3000 next. And I just got, yeah, see, this is going to make sense. I just got 78,000 exactly for that one. So I did them both in a graphing calculator, which made it a lot easier. First, I plugged in 3001, and then I plugged in 3000. And the first answer was $78,010.995, and then the other was 78,000. So if you subtract these two, all of this cancels out, and you literally get 10.995. See how close to 11 that is? So that's the point, is the tangent line can approximate the secant, what's going on in the secant line. And if you round that to the nearest cent, 10.995, the 5 is going to bump up. The 5 is going to bump up this 99 and turn it into 100. So you literally get 1.00 for those three parts. Think of 99 adding 1 and turning it into 100. Because this is 5 or higher. If this was 4 or less, I would have left it 1099. But it actually bumps up to 11. And that's the same as we got in part B. That's the whole point. It's not exactly the same, but it's very close. Especially when you have such large numbers like this. The marginal revenue gives a good, very good, in fact, it was very, very close, a good approximation of the actual revenue, because marginal revenue is very close to. Not exactly the same, but very close to the actual revenue. Well, maybe they mean rounded, it came out the same. I wouldn't say that it's exactly the same, though. If I went to the more decimals, it wasn't exactly the same, but maybe in terms of dollars and cents, it's exactly the same. Okay. So sometimes you have to get these wrong to see what they want exactly, but so that's how you do part C, is you have to do, it's not just R of 3001, you have to do R of 3001 minus R of 3000. And if you get stuck at any point like I did, just view an example that can help you get unstuck sometimes. They're trying to take what you've learned in this section and apply it to some realistic problem, even though this is probably made up too. Okay, so we got 100% of section 3.4, and it took a little less than an hour and a half this time, so that's perfect. And then next time we will be up to chapter 4 is coming up next. And the good news is all this stuff that takes a long time to do in the definition of a derivative, there's techniques for finding derivatives that go much, much faster. So the nice shortcuts are coming up next, and then it's all about memorizing some rules for specific types of derivatives. That's as far as the next test goes. So we'll see you next time for section 4.1.